Hello and welcome to part 5 of our video series. My name is Alex. I am in the Computer Science 471 Data Communications class at Cal State Fullerton. And today we're going to be talking about the network layer of the Internet Protocol stack. So as you can see, from the 7-layer OSI model, we condense it down to 5 because we're not really looking at the presentation or the session layers, but we're mainly focusing on the application, transport, network, and data link, as well as physical layers. In this video, we're going to be talking about the network layer, which is predominantly IP, and we're going to be using CMIP echo requests using a trace route to, we're going to capture some trace route packets, and we're going to analyze them in Wireshark. So just to kind of backtrack a little bit and just to see what we're talking about, I came up with this in a little analogy. So we can think about this 5-layer protocol stack as being like a train. So we can imagine the application HTTP message being sort of like the cargo on a train, and the transport layer, the TCP protocol, as sort of like the train cars themselves, such as the flatbeds, boxcars, etc. So think about the fact that you put cargo in the train car, and then on top of the train car, that's carried by the network engine, the train engine, which is the network layer, which is your internet protocol, which actually determines it comes from the source and chooses the best route for the destination. And then the link layer is like each train station, and then the physical layer, of course, being like a train track where the actual train moves along. So anyways, getting away from our analogy, let's go ahead and just dive right in. So again, we're looking at the internet protocol, or excuse me, the internet protocol layer, so network layer. And so let's get started. So first thing we're going to do is, well, first of all, I'm on Windows 8.1 right now, and there's actually a built-in function that we can do just for fun. If I just go ahead and go to run and I type in cmd for command, there's a trace RT function that you can actually run with Windows 8. Or actually, I think it was in XP, but you can also do it in Windows 8 8.1. So just as sort of if you're use Linux a lot, you want to look at the man page, or you want to just see the sort of help options. You do trace 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 RT, and then space /?, and you can see all the options available to you. But a typical trace route using this method would be to just type in your trace RT and then type in a website such as www.spacex.com, and Windows will actually perform a trace for you, and it will use IMCP to basically traverse all of the routers along the way to this domain of spacex.com. It'll also show you the IP address of each of the stops, and it will tell you how long it gets to each one of them. And it looks like it does 3 trials for each one. Okay, so that's all well and good, but for this exercise, we're actually going to use something called ping plotter, which actually allows us to set the size of our ICMP messages. So what we're going to do is let's go ahead and do the same thing. So let's go ahead and go to www.spacex.com. And actually, before we do this, we want to make sure that we go to edit options, and we want to make sure that our packet settings are set up here. So we want to go ahead and go to, let's see here. There we go, display. And we want to make sure that we are sending, engine. Yeah, we want to make sure that for this first experiment that we're sending packets. We're gonna send it in 56-byte packets initially, and then we're gonna play around with this number and see what happens. So the first thing we're gonna do is we're gonna go ahead and go to spacex.com. We're gonna go ahead and just do wait 5 minutes. We're gonna go ahead and only do this for 3 samples. And so before we do that, we can see our Windows trace RT is just completed. Shows us that it took 7 hops. Anywhere between 25 to looks like 30 milliseconds microseconds for each hop. So yeah, let's go ahead and go to Wireshark, and we're going to capture this packet. So I'm just going to hop on my Wi-Fi here. And okay, so we're running Wireshark right now, capturing packets. So let's go ahead and perform this trace with 56 byte packets. You can see that I perform the same number of jumps, and we're going to do it a couple times. And we're just going to wait for all the data to be collected. And that should be sufficient. Okay, so let's go ahead and stop Wireshark. And let's just take a quick look at what we got. So if we're looking at our Wireshark packet capture, we can see that we're using the ICMP protocol here. And the first thing we want to do to kind of like analyze what we've just done is we want to find the first sort of packet that was sent out for this ICMP echo. And you can see in Wireshark, it's an echo ping request right here. And all we're gonna notice for right now is that look at the TTL value, and that for each. Actually, you know what? Let's go ahead and change this source so we can see clearly what we're looking at. Okay, so the source is obviously from my computer, and yeah, so we can see that the TTL is incrementing by 1 for every echo request sent. And we can also see, if we look at the actual, if we expand the details here in Wireshark, we can see that, well, if we just kind of scroll down, or if we just kind of like arrow down here, we can see that the time to live increments, that value changes. We can also see that the identification value changes, and this reason being that each one of these ICMP echo requests is what's called a datagram. So going back to our initial image that we were kind of talking about here, HTTP referred to as messages, TCP are referred to as segments, IP are called datagrams, and datagrams are sent over the data link layer via a physical means such as Ethernet or wireless or fiber optic, and then it moves back up the protocol stack. So we're looking at the IP layer. So we're looking at datagrams. ICMP sends datagrams, and we'll basically send out one datagram with a TTL of 1. So TTL meaning time to live. So it's going to go to the first router it runs into, and then it's going to be decremented by 1 by the router, and then it's going to quote unquote exceed its time and return back to our machine with the IP address of the router that it came from. So as you can see, the first one, TTL1, TTL2, it means it's going to make 2 hops and then return to us, TTL3, 3 hops, so on and so forth. And we can also notice that the sequence number is also incrementing by 1 each time a new echo is sent out, a new request. And we can also see that we're, of course, using the ICMP protocol. And we can also notice that the identification numbers right here, I want to say they are incrementing by 1, and indeed they are. So 07F9, this of course is in hex, or you can see the decimal value 2041. And if we go into our next echo request, 2042, 2043, etc., etc. So yeah, so that's great and all, but what does that mean? Well, it means that if you're wanting to troubleshoot your network connection, like maybe you think like you have a problem with your router or something like that, doing a trace route is a great way to troubleshoot that and to see if you're even able to send any packets, any datagrams over to the to any following routers. So okay, so great. That was with a 56 byte packet, as you can see from the total length field right here. So what happens if we try to send larger packets? Well, I don't know. Let's try that. So let's go ahead and go back to our options, edit options in the Ping Plotter program. And by the way, this is free for 30 days. I'm just using the 30-day free trial right now. And we're going to change our packet size in bytes to, well, we can test it with 2,000, but let's go ahead and just skip right to a large packet size of 3,500 bytes, which is, of course, 3.5 megabytes. Well, not strictly, because, you know, megabyte is 1024, so whatever. There's probably lots of debate about that. And so, okay, let's go ahead and try the same trace with the same trace route using Ping Plotter to the same domain name here, spacex.com, with $3,500. Whoops, let's go ahead and try that again. reset, restart. So we're using our 3500 byte packets, and you're going to notice that the destination address is unreachable. And actually, hold on a second. Let's pause this. I actually will restart my packet capture here, and let's try that again. Reset, restart. And we're going to come to that same problem, destination address unreachable, but you're still going to see all these echo requests. So let's go ahead and stop our ping plotter, and let's go ahead and stop our Wireshark, and let's look at what we got. So I'm going to look at this based on source. So I'm going to look at it from my IP address, and I'm also going to look at it based on time. So from the time we started the Wireshark packet capture. So let's see if we can find our first ICMP echo request, which is right here. But if you notice, I have a couple red bars here as well, and it's giving me a fragmented IP protocol. So what does that mean? Well, if we notice in our length here, it goes only as high as 1,514 bytes. We'll notice that when we look at our datagrams here, that first of all, it's saying that this frame number 7, or this packet number 17, is reassembled in number 19. So of course we were sending 3,500 byte datagrams, but these lengths are only 1514, and that's not even including the 20 bytes required for an IP header, or so everything minus the 20 bytes of the IP header data is only 1480. So that means that there's 14 bytes also being used for the physical layer or the link layer as part of their header. So what we can get from this is that, well, we can notice that if we look at the identification number here for these, well, let's look at packet number 17 here. If we look at the identification, we can see that it is 2161 decimal. But we can also notice that the total length is 1500, and we can see that, well, the time to live is 1, so this is our first echo request that we've sent out, but it's part of a segmented packet. How do we know it's segmented? Well, if we look at the flags field of the Internet Protocol of the IP header, so the flags field can be found. If we look at the IP header, if I'm just looking right here on Wireshark, if I just highlight it, it'll show me the beginning of the header right here. So this is actually, this sort of gray shaded area is actually the entire header of the datagram. Actually, I'm sorry, that's incorrect. It is part of the datagram header. But most importantly is this flags field right here, this 20 hex, which actually shows that there is the 1-bit flipped for more fragments. So in the third field in the flags part of the IP header is flipped to 1, indicating that there are more fragments following this IP datagram. And so what we'll notice is that there is 2161 is the identification number. And if we look at the next IP datagram, the next part of the fragment, which is number 18 here, and we look at the identification, it is still the same number. So also notice the frame offset, or excuse me, the fragment offset is also different. So basically this first datagram is too big. It's 15 bytes, or excuse me, 1514 bytes. We wanted a 3500 byte echo ping request. Looks like it only wants to send 1514. So the total length is 1500, that's as much as it's going to go. The more fragments field of the flags part of the IP header is sent, indicating that there are more fragments following the packet, this one fragmented datagram, and also that the fragment offset is 0. Fragment offset being 0 means that this is the very first datagram in the fragmented packet. If we look at the second one, still has the same identification number, 2161, same length, 1500. It is maxed out. This is a second fragment. We can see that there are more fragments to follow, and we can also see that the fragment offset is 1480. 1480 being the actual size of the data from the first one, as we can see right here. So after 1480, that's our second packet. So then we look finally at our completed echo ping request of 3,500 bytes, which will show that in the flags field that there are no fragments following this. So this is the end of the first packet. Still has that time to live, same time to live, still has the same identification number, 2161. And amongst other things, of course, like all other datagrams in this traceroute application, ICMP protocol, it's going to have the same source to my computer. It's going to have the same destination, spacex.com, and it's going to be carrying, well, the payload is going to be part of a fragment. So yeah, and as we can see as we go, this is our second packet right here. We can see that it is because, first of all, these are fragments. We can see that this TTL right here is 2. So that's our second one. Here's our third one, fourth one, fifth one, and so on. And actually, as you can see, we've actually experienced some TCP congestion control based on the fragmentation from the first few packets. So we can see that it was a slow start, TCP slow start, and that it only allowed for a window size of X length, which I guess in this case was 1500 or 1514 right here is indicated. But as it kind of got humming along, it looked like that these, I mean, they're still fragmented, it looks like, but for one reason or another, it's not showing that it's considered some sort of error or some sort of warning. So this must have been when the TCP window was increasing after a slow start period. Yeah, so as you can see, this is this is how we do a packet capture of an ICMP echo ping request, or otherwise known as a trace route. And benefits being that it is great for troubleshooting if you have a router that you're not sure is working, or if your internet connection is not working, you want to make sure it's not the router. You could always do a trace route and see if it even gets past your router. Otherwise, this is also combined with Wireshark, is a great educational tool of kind of seeing how the internet works, or just one part of the internet works. So again, this is the network layer, the IP layer, the IP part of the TCP/IP protocol, and we used ICMP, which is Internet Control Message Protocol, to look at echo ping requests, and so using a trace route. TTL being time to live, and each one of these requests showing me the IP address of where it came from after its TTL is exceeded. We can see the TTL being exceeded with these sort of like black colored bars here, and these actually indicate TTL of 255, and I think, if I'm not mistaken, they all are this. Excuse me, they all are the same. 255, yeah. And the reason this is actually because, well, first of all, these packets that I'm looking at right now were the first ones to return. So if I look at all of the ICMP return packets, these are shown in black. We can see that they will have, well, first of all, these are fragmented also. Oh, yeah, these are, wait, I'm sorry, these are not fragmented. But you can see that the TTL are all the same right here. And the reason that is because these all came from the same router. So, I mean, if you think about, I send one packet to let's say I want to send one packet to the first router. It comes back with a certain TTL. I send a packet with a time to live of 2 out to my destination. It hops to the first router, hops back to the second router. As the first packet returns, the first data packet returns, it'll have the same IP address and TTL of the previous first router that it came from. So every time it comes in the first router, the data is going to be the same. All the data from the second router, when it comes back, is going to be the same. And third and fourth and fifth and sixth and so on. So yeah, so that's the time exceeded. And yeah, so this is kind of also a look into just fragmentation, IP fragmentation, and what fragmented packets look like, what to look for if you're looking at Wireshark and you kind of want to get like a sort of, if you want to get an analytical view of it, you can actually look at, like the fragment offset to see that it is not, or to see that it's not the first packet in the fragment. And yeah, and of course you can just see on Wireshark, it kind of conveniently lists it out for you where it is fragmented. But yeah, so this has the same time slot of 255. So this one's coming back from the same the same router 255, but this is the second router returning, the second router hop returning, or I guess it's still the first one, 155. Anyways, so yeah, this has been the fifth part of the series using Ping Plotter Pro and also Wireshark, and also using the traceRT command in Windows 8 to do a trace route. So thank you again so much for listening, and thank you. We'll see you next time.